Well, that last video was a little bit long, so let's see if we can make this video a little bit shorter. This is the second video for Chapter 23, dealing with electric fields. In this case, we want to look at the electric field of a continuous charge distribution. So the electric field would be equal to our famous K constant, integral of our dq over r squared. What we're going to do is we're going to treat our continuous charge distribution as a distribution of many little point charges, all of them values of dq. And then we're going to superimpose those together. So the electric field due to a continuous charge distribution is the vector sum of all the fields due to all the elements dq of the charge distribution. Superposition. So if we just treat them as all little point charges, add them all together, and find out the result, that would be the electric field due to that continuous distribution. Sounds good. For a uniform volume distribution, our dq is going to be equal to the volume density of charge times the change in volume. So our volume density is rho times the dV, change in volume. That will give us the total charge in that volume. For a uniform surface distribution, it will be our surface charge density, sigma, times the change in area, dA. And for a uniform linear distribution, it would be our linear charge density, lambda, times dx. That will give us our charge along that line. Or if it were a curved linear distribution, it would be our lambda, the charge per length, times the length of the arc, which would be the radius of the arc times our change in angle, d theta, in radians. So that's just the charge per length times the length of the arc. So lambda is our linear charge density, sigma is our surface charge density, and rho is our volume charge density. Let's try the linear charge density example first. A rod of length L has a uniform positive charge per unit length, lambda, and a total charge Q. Calculate the electric field at a point P along the axis of the rod, a distance d from one end of the rod. See figure. Here's our rod. It's got a length L, and we want to calculate the electric field at distance d from one end of this rod. Now we're going to evaluate this due to every little piece dq of this rod as we go along. Now the charge on any little dx piece of this rod is going to be equal to the charge per length, lambda, times that dx. In other words, lambda is the total charge per length on this rod, so that would be q divided by L. But equivalently, I could say that lambda is the infinitesimal charge dq in an infinitesimal dx. That's the same charge per length at any particular point. So dq dx is equal to lambda as well. Lambda is a constant for this particular rod. So we're going to say that our E field is going to be due to the contribution from all these dq's along the length of this rod, from 0 to the length of this rod, or from one end of the rod to the other end of the rod. So our dq is lambda dx, and we're going to evaluate from x equal d to x equal L plus d. But dx over x squared, the integration of that is just a negative 1 over x. So we're going to evaluate this, lambda being a constant, k times lambda, negative 1 over x from d to L plus d. That's going to be negative 1 over L plus d minus a negative 1 over d, which we can write as k lambda 1 over d minus 1 over L plus d. Let's find a common denominator for these two fractions. So we'll multiply the first one by 1, L plus d over L plus d, and the second one by d over d. And we get in the numerator, we're going to end up with L plus d minus d. So the d's cancel out. And we have k lambda times L over d times L plus d, which we could write as k lambda L over d plus times L plus d. But the lambda is the charge per length, and if I multiply that by the length, I'm just getting the total charge on the rod. So we have k times the total charge over d times L plus d. That is the E field, a distance d away from one end of our rod of length L. It's independent of lambda itself because ultimately we're just looking at the total charge Q on the rod. Let's try it for a ring of radius A. We have a ring of radius A has a uniform positive charge per unit length with a total charge Q. Calculate the electric field along the axis of the ring at a point P lying a distance x from the center of the ring. So here's our ring of charge, and we have an infinitesimal amount of charge dq all the way around this ring. And we're going to treat each dq as a point charge and find the contribution from every one of those dq's as we go around this ring. Calculus, right? So the infinitesimal amount of E field due to every infinitesimal amount of charge is going to be k dq over r squared. And we're going to find as we go around this ring that those E fields are going to be along the line of action to that point from every low dq. So we're going to form a cone of dE's as we go around this ring. We'll find that on this cone we'll have a component going this way, and then opposite that we'll have a component going that way. And the perpendicular components of these dE's are going to cancel out because one's going to be going one way, the other one's going to be going the other way. As we go around this cone, all those are going to cancel out. So only our x components are going to survive from being canceled out as we go around this ring. So we're just going to look at the x components of these contributions, which will be k dq over r squared cosine theta. And if I look at this triangle, theta is this angle right here. Cosine theta will be x divided by r. So we have k dq over r squared times cosine theta, x divided by r, which would be k x dq over a squared plus x squared to the 3/2 power, because r, which is the hypotenuse of that triangle, is equal to a squared plus x squared square root. So r cubed is going to be a squared plus x squared square root to the 3rd power, or a squared plus x squared to the 3/2 power. We're going to integrate this all the way around this ring, so we're going to integrate over all the dq's around this ring. We'll note, though, at our particular point P, that a is not going to change, and x is not going to change if we've selected a point P, a distance x away from the ring. So those are constants, actually. I'm going to take those out of the integral, x and a, and I end up with k x over a squared plus x squared to the 3/2 power, and we're just going to integrate dq all the way around the ring. Well, that's just the total charge on the ring, so my integration of dq across the ring is just my total charge on the ring, q. So this is kxq over a squared plus x squared to the 3/2 power. And that is the electric field, a distance x away from a charged ring of total charge q and radius a. Note, if we're far away from the line of charge, in other words, if our distance d is much greater than the length of the line of charge itself, our first expression for the line of charge, if d is much bigger than L, then L is insignificant in the denominator here, and we will get that our E field will approach kq over d squared, d being our distance from the line of charge. And that is just the value of the E field of a point charge if you're a distance d away. So if we get really far away from the line of charge, it starts looking like a point charge. And if we get really far away from the ring of charge, such that x is much bigger than the radius of the ring, a, then in the denominator here, x squared will be much bigger than a squared. So I'll have x squared to the 3/2 power, which would just be x cubed, and then have an x in the numerator, so one of the x's will cancel out. And I get that if I get really far away, my E field approaches kq over x squared, which is also like a point charge. So if you get far away from the ring of charge, you'll find that it starts looking like a point charge. How about that? So as we move far away from the geometry of either of these objects, a line of charge or a ring of charge, the field is indistinguishable from just a point charge of the same value. This is so much fun. Let's try another example. Let's find the electric field of a uniformly charged disk. This is something that's going to be very important to us a little bit later on. What we're going to do is use the result we got for a ring of charge and then apply these rings all the way across the radius of this disk. So our dq is going to be equal to our surface charge density sigma times our change in area. But our change in area is the area of each of these rings, which will be the circumference of the ring, 2 pi r, times the thickness of the ring, which is dr. So we have 2 pi r dr is our change in area. Using the previous result that we got for each ring, we find our dE in the x direction is going to be kx dq over x squared plus r squared to the 3/2, r being the radius of every one of these rings, but now that's going to be a variable because we're going to go from 0 to the total radius of this disk. And our dq is going to be our surface charge density, 2 pi r dr. We're going to integrate this over the radius of this full disk, take out our constants. So we have kx sigma 2 pi, evaluate this integral from 0 to the radius of the disk, r dr over x squared plus r squared to the 3/2 power. That integration is actually a negative 1 over x squared plus r squared to the 1/2 power. In other words, if you took the derivative of this result, you would get what's inside the integral here, r dr over x squared plus r squared to the 3/2, as you decrement this negative 1/2 in the denominator. So we'll evaluate this from 0 to r, the radius of the disk, and we have that this is 2 pi k x sigma 1 over x minus 1 over x squared plus r squared to the 1/2 power. Or if I factor in the x, I have 2 pi k sigma 1 minus x over x squared plus r squared to the 1/2 power. All right, cool. Note that if r is much bigger than x, in other words, if you're not very far away from this disk, or if the disk is infinitely large and you're kind of close to this disk, then this second term becomes basically 1 over infinity, and that's going to be 0. So if you're relatively close to this disk, the E field will become basically a constant, 2 pi k sigma, or since we know k is 1 over 4 pi epsilon naught, this will simplify to sigma over 2 epsilon naught. So if this disk is infinitely large, or if you're really close to this disk, you have basically a constant E field equal to the surface charge density sigma divided by 2 times a constant epsilon naught. How about that? So a constant electric field close to this disk. Let's try out a problem with this disk. Consider a disk of radius 3 centimeters having a uniformly distributed charge of 5.2 microcoulombs. Compute the electric field at a point on the axis 3 millimeters from the center. Compare this answer with the field computed from the near field approximation that we just got, which is sigma over 2 epsilon naught. Well, our sigma in this case is going to be the total charge over the total area of this disk, q over pi r squared. 5.2 microcoulombs over pi times the radius of this disk, 3 centimeters squared, is 1.84 times 10 to the minus 3 coulombs per meter squared. In the near field approximation, the E field will equal 2 pi k sigma. That's going to be 2 pi times 9 times 10 to the 9, and we just figured out sigma to be 1.84 times 10 to the minus 3 coulombs per meter squared. So this will be E field of approximately 1 times 10 to the 8 newtons per coulomb. If we actually put this into our exact result, that'll be 2 pi k sigma 1 minus x over x squared plus r squared to the 1/2 power, 1 minus 0.0033 millimeters, or 3 millimeters squared plus 3 centimeters squared to the 1/2 power. And that comes out to be exactly 0.94 times 10 to the 8 newtons per coulomb. So not a whole lot of difference. I mean, if we calculate exactly for 3 millimeters from a 3 centimeter radius disk, we find that it's very close to the near field approximation as it is for a constant field. Cool. I like that result. Compute the electric field at a point on the disk 30 centimeters from the center of the disk. Compare this result with the electric field obtained by treating the disk as a 5.2 microcoulomb point charge at a distance of 30 centimeters. So we're going to move far away from this disk and calculate the field there and compare it to a point charge. Well, the exact value is 2 pi k sigma 1 minus x over x squared plus r squared to the 1/2 power. And x in this case is 30 centimeters or 0.3 meters. And if we calculate that, we get 5.16 times 10 to the 5 newtons per coulomb. But if we treat this disk as a point charge, because we're far away now, 30 centimeters is far away compared to a disk of radius 3 centimeters. So we're something like that. The point charge will be just kq over r squared. That's 9 times 10 to the 9 times 5.2 microcoulombs over our distance away, which is 30 centimeters, 0.3 meters squared, 5.2 times 10 to the 5 newtons per coulomb. So as we get far away, it looks very much like a point charge, and we can't distinguish this disk of charge as being just a point of charge. Nice to know, because we can use that approximation for many things if we get far away from the object itself. This concludes our treatment of distributions of charge and the E field due to those in the second lecture of Chapter 23, and we'll conclude there.